or are listed below. Questions and comments to the experimental work. I will just give some, I don't know if I need to read all of them or...
No, it is up to you.
Okay.
If some questions are answered already here,
okay, so...
not necessarily.
Okay, so I will just kind of read only those which are kind of most important from my point of view. Okay? Okay, so once more, I did not find in the presented thesis the detailed discussion how the fabricated sensor analytical performance compared with methods described in literature. The author indicates advantages of device sensors in comparison with established method used in antibiotics determination. However, there are numerous sensors for amoxicillin described in the literature, many of them not involving MIP as a recognition layer. However, the author discusses only the antibiotic sensor using MIP technology. See Table 1 and Section 1613. The other types of sensors have been described, mainly for amoxicillin, giving examples. Also for sulfamethiazole, there is a paper describing zinc oxide nanorod-based chemical sensor for this antibiotic. Actually, it is, I'm not sure because the author in the thesis is referring to using NMR diffractometer. I think this is an error. This should be rather spectrometer. Okay. Okay, there is a lack of detailed information regarding the soldier procedure of MIP for field formation in the experimental part. This rather vague description of this procedure without a lot of details. This is strange, especially in view of lack of this method description in the publication form of the basis of the thesis. There is actually a question regarding the Sauer-Bray equation. The Sauer-Bray equation is valid for film rigidly adhering to the resonator. So care shall be applied when interpreting frequency change in terms of mass change. I wonder if the resulting film thickness here was validated by some independent method, for example, ipsometry, or if the rigidity of the deposit field has been validated. I missed the rationale for use extraction procedures here. Why acetic acid methanol with what the ratio 1 to 1 to 1 to 3 has been used? So it was optimized somehow, or it's just taken from the literature as the basis.
So are you waiting for answers now?
No, not really. I'm just kind of giving. I understand
okay.
that you have my report, so you can.
Okay.
So I'm just. Or if you prefer, I can write for the answer. I don't know how the procedure.
So if you are aware, need that there is question, then we have to answer.
Oh, okay, so maybe we'll do that way. So this question regarding Sauer-Bray equation, did you check this one with some other methods than this of gravity?
Yeah, sure. I agree with you that the Sauer-Bray equation is only holds for very rigid fins. But in Article 2, it was also stated that this thickness was actually confirmed by ellipsometry measurements. So what we did was just to make with a frequency decay every time reproducible fin thickness. So, but the main thickness was actually detected or measured by ellipsometry measurement. So yeah, it's quite correct that the Sauer-Bray equation holds for rigid fins, and then so the thickness measurement between from 1 to 1 should be. But of course, if you have the same polymer film synthesis, then the rate of frequency decay should be the same at all times. So this was for me.
Yeah, I understand that this is important, but well, it would be interesting to see how the, let's say, ellipsometric thickness compares with the thickness calculated from Sauer-Bray equation. It is kind of giving exactly the same values, or it's kind of there is a discrepancy between this. So this would be interesting in thesis. Okay. Then this question about the use of extraction procedures. Why the extraction procedures? Will they optimize somehow, or just take it from, let's say, literature, this would work better, best?
Yeah, actually, the acetic acid methanol mixture ratios of mixtures have been used widely to disrupt non-covalent interaction that exists between the monomer and the template molecule. Now, why different ratio? Because initially we tried with 1.3 for SMZ MIP, supplemental MIP, and then we, as I showed, so that the regeneration procedure have like a decreasing signal, following rebinding regeneration cycles. But so this was thought to be probably too harsh, treatment for the polymorphin, and so the ratio was reduced to 1:1, just so as to check, what we. So this was actually the difference in ratio. But actually, the way to remove the template molecule is to look for solvents or solvent mixture that is able to dissolute the template molecule in it, and then it will extract or remove the template from the cavity of the polymer.
Okay. In general, I did not find in the thesis information if NIP films were treated as NIP before rebinding studies or not. Like, this is kind of an important point because in certain cases, the rebinding procedure may also alter the structure or morphology of the film. And then, of course, the comparison between NIP and NIP becomes kind of difficult. So it's not clearly written in this thesis. So
yeah, maybe I agree to some extent that maybe not clearly written, but if you check section 1.7 of the thesis, so there was a mention, and all through all of the publications, there was a mention that the NIP film only differ from the MIP only in the use or exception of the template molecule or the preparation. So because for us, they have to be treated the same way, so as to ensure reliable analysis between the MIP and it. So this is a reference NIP. So if the reference is treated differently, then you cannot actually, make a reliable conclusion on what is happening. So all of the papers. So it's just that maybe paper 1 and paper 2 or paper 3, section 2.3, actually gives more, attention, as to this, this statement. But all of the papers contain this information as to the fact that the MIP and MIP only differs in terms of the inclusion of the template during the preparation.
Okay, so let's answer my question. Okay, this question of this description of quantum chemical calculation is once more rather vague in comparison to the publication. There is no mention of the calculations of complex with different than 1:1 template monomer ratios, which were performed actually for the publication 1 for the sulfamethiazole. Then there is a question, the same calculation was performed for amoxicillin. I could not find any information about neither in publication, neither in thesis. Okay. Okay, there is also question, practical, why sulfamethiazole NIP deposition molar ratio of template to monomer was 1:142 instead of 1:2 as predicted by calculations.
Yeah, so like 3 questions in a row. Yeah, firstly, the quantum chemical calculation is done by first to generate the complex between the monomer and the template molecule, and then you optimize the geometry of the empirical methods. And then the last thing, just like so this is like optimized geometry, and then the last is to calculate the binding energy. So the binding energy is actually calculated, is actually calculated by taking into account the different possibility of hydrogen bonding formation. So if you see in the case of sulfametazole, so there are 2 proton acceptor groups, 1 and 2, and then so what we did actually was to between ratio 1:1 and 1:2 is actually to check. So ratio 1:1 we show you the binding energy. We always show the affinity of the template to the monomer, while the ratio 1:2 is actually the fully saturated form of this complex in solution. So I mean, like,
I would not agree with that, to be honest.
Maybe because
no, because you are assuming that the only binding possible is through hydrogen bonding, which is is not true.
Yes,
Because you
I know that. I mean,
stuck-
for quantum chemical calculation, it only takes into account hydrogen bonding.
Well, it depends how you calculate. Because if you set the calculation that way, it will count only for hydrogen bonding. But the question is, what will happen? Calculations are, not to say easy, but they are patient. So if you add another molecule and try to calculate, you will get some results. The question is what those results will be. So for example, if you go for the complex ratio 1 to 2 to 3, you may have still increase of binding constant, or delta G of the complex formation, but the, let's say, next molecule may not necessarily bind to the hydrogen bond. It may bind to the target amino acid by pi stacking, which is fully possible in view of presence of benzene ring in the analyte and in the monomer. So this is why I'm asking about the.
Yeah.
I know that this is difficult because theoretically you should calculate a very broad range of structures, yeah, which is difficult to get in resonable time. So some assumptions need to be taken. Let's say question is then the question arrives: why stop at this point?
So because, like I said, so there are two only proton accepting groups in sulfur-methyl, and so the highest stoichiometric ratio possible will be that two molecules of the monomer will react with one molecule of the sulfur-methyl. And so this is why 1 to 2 was calculated. If you look at the ampicillin, so you have 1, 2, 3, 4, 5 acceptors or proton acceptor centers in the molecule. And so it will mean that if you want to start calculating, you calculate for 1 to 1, 1 to 2, 1 to 3, 1 to 4, 1 to 5.
Yeah.
And this, because you know that the saturated, fully saturated complex will actually be that 5 molecules of MPD will react with with 1 molecule of carbon. So this is why we went to actually the fully saturated complex. So the ratio you found in the thesis was actually not 1 to 1, but actually the fully saturated complex. And if we put in ratio, it will be 1 to 5.
Mm-hmm. Okay. Okay. Then I will move to another question. Sorry, we have quite a few of them. Okay. Application of spectroscopic techniques for prepolymerization complex formation studies is a very promising way for rational nuke design. Therefore, UVTs and NMR studies described in the presented thesis are of great value. However, I wonder why the UV studies of amoxicillin and diamine complex formation were not extended to regular UV titration, because then you would get kind of experimental information about the ratio of monomer to diameter from this. As there is a shift of UV's bands for complex, so then it should be possible to follow this binding directly in solution. So then you will get just precise information what ratio you should use to get the best bindings polymers.
I agree with you. Actually, it was a regrettable oversight. So it wasn't.
I understand that you cannot do everything in one paper. I'm also wondering why proton NMR was not used, because the proton NMR would be more sensitive to the binding.
It was carried out, so it was just not shown in the thesis or in the article. Why? Because we already confirmed by now you say that by computational study, so hydrogen bonding interaction, and then the why carbon 13 was used was just to show if there was any kind of covalent interaction. So this was carried out, it was confirmed, so the result was confirmed, the computational result was confirmed by the proton NMR, but we want to be sure if there are some kind of covalent interaction that happens also. That was why we presented the carbon 13 NMR spectra as with rather than the proton NMR.
Okay, and what follows from this?
So from this, what we see is that there is a shift in spectra between the.
You have quite substantial shift.
Yeah. So and then we can for sure say that we have a hydrogen bonding in fact.
Yeah. Okay. Thank you. Okay, I wonder why the language for the isotherm was used for the fitting of the results of analyte rebinding with poly MPD fields. Did you attempt to use any other isotherms or compare the binding or how the isotherms fit with different isotherms as you did use for this hybrid organic field?
So yeah, I was just looking for So all of the MIP films, the extensive MIP, thermomip, and hybrid thermomip films were fitted with all of the three isotope models. And then, like I said before, we found that the Langlois friendly gave the best fit. And I think the reason is quite understandable. Why? Because the Langlois model is based on the assumption that all binding sites have the same binding energy. Which in the case of MIP may not be entirely true. But also the friendly, which was actually designed to cater for heterogeneity in surfaces. But in the case of MIP, it doesn't fit so well the what is it called, the plateau of the complex. And then it's restricted to just very small concentration range. So this is why it doesn't always work for all of the MIP. But the Langlois friendly can, ask the tendency to be shifted if you apply properly between the Langlois and then the friendly model. And so this is why I think work well for all of the MIP.
Why not, for example, BET isotherm?
Well, we didn't try. I tried.
Okay.
We didn't try
different. Quite a range of isotherms.
Yeah.
I understand that if you go for very complex equations, so then you can fit everything to everything. This is a problem. So if you go for very detailed or very advanced isotherms, then they start to you can fit everything with that, which is not really making sense.